Welcome everybody to episode 19 of the Quantum Science Seminar. Today's all going to be about atom arrays. And as usual, we would like to have your questions. So please send us your questions via email to quantumscienceseminar@gmail.com, or please use the YouTube live chat at the right or at the bottom of your screen. Our speaker kindly agreed to take a break sometime in the middle of the talk so we can start answering some of these questions. And as you know, we typically have many more questions than we can answer. So Misha also very kindly agreed to stay on after the talk. And I will share, at the end of the talk, we'll share the Zoom link to our meeting here. And you're welcome to join us and interact with our speaker for a bit. Please also note there's a 30-second time delay between what we're doing here and what you're seeing on YouTube. And with that, I would like to hand over to Ofer, who will introduce our speaker today.
Thank you, Sebastian. Good afternoon, everyone. It's a pleasure for me to introduce today's speaker, Professor Mikhail Lukin. Professor Lukin did his PhD and postdoc in Texas A&M before moving to Harvard. He was an ITEMP fellow and later a joint director of ITEMP. And for many years, he is now a professor of physics at Harvard University. He is a member of the U.S. National Academy of Sciences and has received many awards, including the Adolf Lomb Medal of the Optical Society of America and the Isidore Rabi Award of the American Physical Society. His research spans a wide range of fields, from quantum optics to many-body physics and quantum information in atomic and solid-state systems, and he made pioneering theoretical and experimental contributions in all these fields. Two of my favorites are the development and demonstration of coherent storage of light in atomic ensembles, and more recently, the realization of strong photon-photon interactions using Rydberg polaritons. And when he jokingly compared Rydberg polaritons to Star Wars lightsabers, he was announced on a national radio show as Professor Luke Skywalker. So without further ado, it is a pleasure to host Professor Lukin today, who will talk about programmable quantum systems based on Rydberg atom arrays. Misha, thank you for coming. The stage is yours.
Thank you. Thank you for a very nice introduction. So, I mean, I should say here, for the record, that Ofer had a role to play in this lightsaber idea, so I cannot take the credit or blame for that, So, I would also like to thank Sebastian, Ofer, Andrew, and Christian for actually, pushing forward and maintaining this great seminar series, and basically helping us all to stay connected. So what I will do today, I will talk about our efforts and what we kind of think about the quest for controlling quantum world. So I guess this is a common theme for this seminar series. Here, what we are trying to do is isolate and control some simple quantum objects and then build more and more complex systems from them. And what we'd like to do with them is explore new physics with these engineered quantum many-body systems, basically creating and probing new quantum states of matter, and also explore new applications. And applications are quantum information processing, metrology, communication. So all of these kind of basic physics directions and the applications and technology development are intrinsically connected. So each of these fuels the other. And at the end of the day, the big kind of question that we are trying to answer with them: can we build truly large scale, truly quantum entangled systems? And what can we use them for? Can we use them for interesting scientific or technological application? And kind of the way where this field is, I like to think about this as a kind of quantum rivalry, and one can think about different things these days, it's a competition maybe between different platforms, between different groups, but actually it's at the end much more kind of basic, much more fundamental, in the sense that it's a competition between two forces of nature. One is controllability and another one is scalability. So if you have a small system or small organization, it's relatively easy to control, but when it becomes large, it becomes harder and harder to control. And it's true in many aspects of life, but actually it's true in particular in the case of the the quantum system. So the frontier is that we would like to really build systems which implement tasks which modern classical computers cannot do, and typically you need kind of an order of maybe 100 or so of qubit systems, and we are also asking a question: can this task be kind of useful for humankind? And this is kind of a direction of basically you have to think about useful algorithms and applications. And for systems of this complexity, at least right now, to really implement them, you kind of have to think about co-design. You have to think about application and the system, controls and your physical systems all together. So with this kind of idea, what I would like to do today is give you a little bit of a sense of what we are doing in the domain of the Rydberg atom arrays. So I will tell you about a little bit, how we can assemble arrays of regular arrays of atoms and how we can control them by exciting into Rydberg states. And I will kind of review of maybe one aspect of our prior work, and this is studying entanglement dynamics, and in particular this idea of many-body scarves, before moving on to talk about our recent work. And our recent work was aimed to kind of scale up, to develop two-dimensional arrays and to start exploring 2D spin models. And if I have time at the end, I would like to give like two scientific examples of the things which we are exploring. One of them would be, extending this many-body scarves work into two-dimension and, looking at stabilizing the many-body scarves. And perhaps I can also give you a little bit of a sneak preview on what we are doing in terms of implementing quantum algorithms. Okay, so our approach to this challenge of building scalable quantum system involves atom by atom assembly of atomic arrays. So we start with atoms pre-cooled using the conventional laser cooling techniques. And what we do is we create an array of tightly focused beams in a vacuum chamber, the so-called optical tweezers, which can trap individual atoms. And we just try to trap them directly from a magneto-optic trap. So, in any given attempt, we will trap a certain number of atoms, and we focus the tweezers tightly enough that in each trap we can have at most one atom. But what happens in any given attempt is some of the traps will be full and some will be empty. And so the system has an entropy, and then to get rid of this entropy, what we do, we just take an image of the atoms and figure out which traps are full and which are empty, and then remove the empty traps and then rearrange the rest of the traps. So with that, we end up with the arrays, with regular arrays in desired configuration, with separation between atoms, which typically in a range of few micrometers. So atoms in these traps do not tunnel between different traps, and they do not interact. So to enable interaction, what we do is we excite the atoms into the Rydberg states, where they have a much larger size, and then they basically start talking to each other. And this project is a collaboration with the groups of Markus Greiner and Vladan Vuletic within our Center for Ultra-Cold Atoms at Harvard and MIT. So this is the first generation of our experimental system, where we focused on one-dimensional arrays, which were created by this device, acousto-optic deflector, where basically for each tone of the RF input, we get one deflection, one beam. And then what we do is we just project these beams in a vacuum chamber. And if you, for example, need to remove one trap, you just remove a tone. If you need to shift the trap, you just sweep the frequency of the tone. So this is a picture, kind of almost historical picture by now. It's basically a first generation of the students and postdoc who built this experiment. So you, of course, guys, many of you know them very well, and many of them already went on to start their own groups. And this picture is historical also for another reason, that something like that, where there are so many people in the lab, has not been allowed in our labs for the past 6 months, and I will return to that a little bit later in my talk. But so these are some of our first kind of rearrangement attempts. So here we try to trap something like 100 atoms, and we try to create 100 traps, and then trap something like 60 atoms, and then basically, you see that in the first shot there is a lot of disorder, and then after rearrangement, the array is much more ordered. So we can, of course, also create some combinations, clusters of 2, clusters of 10, and these are all single-shot images of the atoms. So, so basically, using this approach, we can, create, very nice and kind of regular arrays. So little bit, a few more words about the interactions. So we like Rydberg states to induce interactions for 2 reasons, because they combine, strong interactions. So for example, if you excite the atoms into the state with n equals 100, the interactions are 14 orders of magnitude stronger. The van der Waals interaction is 14 orders of magnitude stronger between these atoms as opposed to the ground state atoms. And these Rydberg states also have fairly long lifetime. So the typical states we work with live for a couple of 100 microseconds. And so this 14 orders of magnitude is a large number, so we can make a good use of that. And one way how we use that is in the context of something which is called Rydberg blockade. So the idea is the following. So if you have 2 atoms which are very far away, you can just drive them resonantly, and they will undergo Rabi oscillations. But if you start bringing these atoms closer and closer, eventually these Rydberg interactions will take over and will shift the doubly excited state way out of the resonance. And so this kind of in this kind of situation, you will be able to excite each of the atoms resonantly, independently, but never atom pair. So that's what's called Rydberg blockade. So basically, simultaneous excitation is block distances smaller than this characteristic size when this blockade takes over this blockade radius. And we like this Rydberg blockade because it's actually a very robust mechanism to entangle atoms. It's insensitive to motion, relatively insensitive to motion, to position, and so on. And it's kind of very strong kind of dominant effect. So at the end of the day, what we will do is we will prepare the arrays of atoms and place them where we want. Then we'll subject these atoms to sequences of these Rydberg pulses, or sometimes we'll use hyperfine states, so we can also manipulate the hyperfine states. And then at the end, we will just make a projective measurement of the atoms, just figure out which state, ground or Rydberg they are. I should say that in addition to our group, there is some very nice work which is being done, by a number of groups around the world. I would like to particularly highlight Antoine's group in U.S.A. and as well as Mark Safman, and also kind of a new generation, for example, Manuel's group at Caltech. So I'll comment on those a little bit later on. So. Okay, so at the end, what we would like to do is we would like to do things like quantum simulation with the systems, and so we can, cast the dynamics of this system in the form of the effective spin Hamiltonian, right? Because, for example, if you use ground and Rydberg as a effective two-level system. And so in this Hamiltonian, there are a few terms. So one of them is basically a Rabi driving. Another one is a laser detuning, and the third one is interaction. And so if you ask a question is, for example, what's the ground state of this Hamiltonian? So this ground state will be controlled by 2 parameters. One is the laser detuning, and another one is effective interaction range. So if there are no interactions, then it's clear that depending on the sign of the detuning, either all atoms should be in a ground state or in Rydberg state. But if you turn in the interaction, for example, if nearest neighbor is blockaded, so then clearly the state like this, will not be accessible. So then, the kind of the lowest energy state you will be able to excite for positive detuning is the one where every other atom is excited. right? So basically this term, the detuning term, tries to maximize the number of Rydberg atoms at this point, and the maximal number you can have is when every other atom is excited. So this is the state which we will talk a lot about. This is a so-called antiferromagnetic state, or a state with Z2 symmetry broken, and so on. So this is what happens if you have just nearest neighbor interaction. But if you extend the range of interaction, then of course you'll have also next nearest neighbor blockaded. Then you will break Z2 symmetry, and then it goes on. So this system already in this kind of simplest form gives rise to quite rich phase diagram, which actually, fortunately, is fairly well understood by now theoretically. And we can explore it experimentally by just preparing all atoms in the ground state and kind of sweeping the detuning, trying to enter disordered phases. And for example, for small system, in this case for 13 atoms, you can easily explore all of these phases by just essentially changing the distance between atoms, effectively changing the effective blockade range. So in this case, this is a state up, down, up, down, up, down. So here is up, down, down, up, down, down, up, and etc. So basically, what we see is that kind of this system that we are working with actually has a lot of control knobs. It's what we say is highly programmable, and we can, for example, program interaction range, and by playing with this interaction range, we, for example, can break desired symmetry. But at the end, what we would like to do is we would like to make use of the fact that we can start with large arrays. So in this case, is 51 atoms. And if we do this adiabatic sweep, for example, going into antiferromagnetic phase, then we usually don't get completely ordered arrays. So typically, we would get images like this, where you have a kind of an ordered domain, and then another ordered domain, and then in between them there are these, kind of imperfections. We call them domain walls. And what you can do, for example, you can look at the domain wall density, at domain wall variance. You can basically explore all properties of these domain walls. And for example, if you go here across the phase transition, then domain wall density kind of varies smoothly. It basically goes from high to low, but the variance actually peaks. And this makes a lot of sense because it peaks at the point where a system undergoes phase transition. It doesn't know in which state it wants to be. So these two states compete. So it results in a kind of a lot of noise. And we can use this kind of technique to identify what the phase transition and compare it with theoretical predictions, etc. So that's one way to look at the system. But there is also another way. And another way is microscopic. So we can look at all possible states, which we can generate. And sometimes we generate perfectly ordered state. And so in this kind of very first experiment, this perfectly ordered state, occurred with fairly small probability, but still it was kind of the most probable from all microstates. And actually, subsequent studies, we tried to kind of improve the system, and now we can hit this perfectly ordered state with double-digit percentage probability. But so this kind of allows us to look at microscopic things associated with these phase transitions and dynamics. So the other fairly convenient approach to characterize these things is look at density correlators. So this is this up, down, up, down, up, down order. And from here, we can, for example, extract typical correlation lengths and stuff like that. So what you see is that we have really kind of, a lot of tools which allow unique, insights into phase transition, quantum dynamics and so on. And over the last 3 years, we actually enjoyed, kind of working with system like this. And we kind of explored both this kind of more kind of macroscopic phenomena, but also looked at a microscopic phenomena. For example, we used it to implement high fidelity entanglement and parallel multi-qubit gate operations, on pairs or triplets of atoms. We've also studied novel quantum phase transitions into these states which break the Z3 or Z4 symmetry. They're actually non-trivial, and we've used Kibble-Zurich mechanism, to kind of explore those, So this is something that I will talk a little bit more about. So we also studied non-equilibrium dynamics, and this was the area where we actually made the first kind of small discovery. And we also use this to engineer large-scale entanglement. So basically, what it really shows is that we can really use this system, which has a large size, but also very high degree of quantum control. And I think together with some other recent kind of advances, for example, like in Manuel's lab at Caltech, he has also now implemented this for these techniques for alkaline earth atoms, and also some recent progress, very recent progress in U.S.A, where they also start kind of improving the coherence in Antoine's lab. So it's actually really these things emerge as, as one of the kind of, I would say one of the leading platform for both analog and digital high fidelity quantum control. So there is one other thing that I want to mention is that, in over the last year or so, there has been an explosion, in different types of tweezer arrays that people now can create with different types of atoms and also with molecules. And I think there is maybe another like 24 of experiments of this type, is now being kind of built. And I think it's really an exciting frontier because it really bridges, quantum computing, quantum simulations, and quantum metrology. In particular, I'd like to highlight, Adam's recent work in GILA, where, they're really building kind of cutting edge, clocks, and also actually manuals, I must say. Okay, so just, I want to give, one example of kind of a new science that we, studied with the system, and this direction involves probing non-equilibrium dynamics. So at a high level, so once we have the system, we can really have an ability to go in all different corners of the big Hilbert space, and explore it. And, kind of far away from equilibrium, this is really something that up to now one could really not study, with any other, system. So this we really can go and explore new dynamical phenomena, and we have done it in two different regimes. One, we studied this kind of near adiabatic evolution, and this is connected to something which is called Kibble-Zurich mechanism. But also what we have done is we try to basically go far away from equilibrium. In fact, in some of the very first experimental runs, once we built the array and had Rydberg control, so the guys at the time, probably Hannes and, Alex, Harry, they just started playing with the system. And I said, well, let's check how the system thermalizes. Let's just take an ordered state and just, quench it across the phase transition. And there we immediately saw some surprise. And this surprise gave rise to something which is called by now quantum antibody scars. So here is kind of the first observation and, interpretation in brief. So essentially what we did is we studied with the, atom chains and, created antiferromagnetic states. So for example, here is a 5-atom chain. You have this up, down, up, down, up, down correlations. And then, what we did is we basically quenched the detuning. We changed detuning just across the phase transition. We changed it to 0, right? And the idea was that at that point, the system should be ergodic. It should kind of equilibrate. And it did and does, but it kind of does it in a very non-trivial way. So for example, these are these kind of trajectories of 5 individual atoms. And so it looks like a mess, but if you look at it for a while, there is some kind of regular pattern. So for example, at this point, so initially you had this up, down order, then this order disappeared and become down, up order. Then you wait a little bit, so original order, reappears. So what you see is that there is some kind of collapses and revivals of this original kind of antiferromagnetic pattern. And we were actually quite puzzled initially. Why was it the case? And we thought, well, it's a small system size, so let's try to do it for larger systems. So this is, for example, domain wall density. What you see is that for 9 or 51 atoms, still this pattern emerges, right? So you have basically quench, and then you have this kind of oscillations of the order parameter. So the reason, and these oscillations have a characteristic frequency, which is proportional to Rabi frequency, but not equal to. So it's Rabi frequency divided by some number close to a square root of 2, but not exactly square root of 2. So what's the physical origin and why is it surprising? So the reason is because, this system, should be at least theoretically non-integrable. So And as such, it should undergo thermalization. So even under perfect blockade, where you in principle cannot access all Hilbert space, the Hilbert space dimension scales exponentially. It's actually downscaled as 2 to the n. It scales a golden ratio to the power of n. There is a reason for that, actually. It's not an accident, but nevertheless, the system should thermalize. So then we started kind of, already early on, kind of trying to understand it. And actually, Hannes and Sun Woon played a kind of major role in kind of this early understanding. So what they have started doing is started doing simulations by using, for example, matrix product states. And what you see, this kind of matrix product state simulation really reproduces the experiment very, very well. But then they also kind of started looking at things like entanglement entropy. And what you see here is that associated with this oscillation is some non-monotonic growth of entanglement and entropy. And that's what's kind of special. In a way, it's sort of obvious that it's something like that should occur, right? So because usually when you do this quench, the correlations start grow. Basically, atoms started getting entangled with their neighbors and so on and so on. But here, something funny happens. The correlations grow, and then the kind of system gets disentangled. The correlations grow, and system gets disentangled. And so this was sort of what we, as much as we could understand at the time before we kind of published our first paper. We also kind of realized that decay is due to long-range interactions, but we basically were not really sure what is this beast, what's this effect, and then basically a number of theory groups started kind of looking at that, and there are several explanations. I will just review one of them in details a little bit here, and this is, I guess, one of my favorites. So this is an analogy between this observation with something which is called quantum scars in a single particle chaos. So what quantum scars are is the following. So if you start with the chaotic classical system, like a billiard, so then what will happen is that most of the trajectories there are just kind of runaway trajectories. They're completely chaotic. But there are a few trajectories here, just from the symmetry considerations, which will be closed. And you could say, well, they should really not play a role if you quantize the system. Actually, it turns out that this is not always the case, right? And specifically under certain conditions, when the period of this orbit is shorter than the Lyapunov exponent, you can identify some eigenstates in the quantum domain which very much resemble these classical periodic orbits. And the idea of this explanation, which is due to Dima, Banyan, Max, Serbin, and their collaborators, is that this kind of phenomena of quantum scars is something what we see in our system, but in a kind of many-body fashion. So what they pointed out is that there is a kind of subset of states in this Rydberg model, which actually is somehow special, right? So basically, if you start with a generic state, the system would thermalize, and that's what we observe experimentally. But there are some states which are really kind of distinguished, and these are these kind of scar states. So I must say, initially when we heard about that, it was sort of not obvious how these two concepts are related, and actually it turns out one can build a nice connection between this different kind of single between this different kind of concepts by using matrix product state. So actually matrix product state provide kind of a semi-classical version for the description of the dynamics. What we see is actually, it turns out if you parameterize these dynamics in just a smallest kind of bond dimension 2 matrix product state, then exactly what emerges are these kind of closed orbits. They are closed but unstable. But the system, can really, once launched to it, can actually live for a very long time in this kind of subspace of states with low entanglement, before eventually leaking out of that. So this is kind of, one way of thinking. There are other ways. So for example, our string theory colleagues, Daniel Jafferis, got very excited about that, and he kind of is thinking about some analogy with that, with particle kind of orbiting around black hole, where entanglement and disentanglement means that particle comes closer to the black hole and goes far away. So it's kind of fascinating analogy. So I think a little bit maybe more quantitative was insight from Marcello's group, who actually figured out a kind of mathematically rigorous connection between these many-body scars to something which is called string inversion and lattice gauge theories. But basically, there are a lot of kind of still open questions, and there's a lot of theoretical work. So this kind of highlights that it's really kind of, going in this kind of deep corners of Hilbert space allows us to really, study kind of new and explore new physics. So I was asked to, stop maybe midway through my talk for questions. So I wonder if this is if it's a good time, So yeah, let me slow down here. I'm happy to answer some questions.
Yes, Misha, we have some questions.
Yeah.
And let me start with one from Bill Phillips. Yeah. Looking at the 51 atom array and the phase transition seen in the variance, the plateau of the variance is quite different on either side of the transition. Is this understandable in a simple way?
All right, so Bill's, of course, always great questions. So let me see if I can find sorry, now I have to, that's the downside of this. Hold on, so let me just, I will go to the slide. So yeah, that's a kind of very good observation. So that, I mean, there potentially could be two reasons for that. So one of them is that, okay, so the variance at the negative detuning, I think it's simple to understand because it's, there the state is trivial, right? The state is just a ground state atom, atoms in a ground state. But if you go to the positive detuning, what happens is that, kind of you have this sort of classical kind of target, state, kind of classical stationary points. But of course, what happens is that whenever you, have the still driving the system with a, a laser with a finite detuning, you will still have some superpositions of the states. And so what I suspect is that this plateau here is a consequence of that there is still a little bit of quantum fluctuations remaining. And for this, this is a simple system, you could say, it's a side effect, but actually with Bill's questions, this is what I always tell my, my students in the class. There are no, there are no questions which are too simple. So if I have time where I will talk about some of the more recent work, you will see that some of these things really kind of play a role. Sometimes these fluctuations indicate actually the presence of new phase. Hope it makes sense. So should I do have a few more questions or should I keep moving? Sebastian, you are muted, I think.
Yes, there is one more maybe. And the question is it clear in which classes of models these many-body scars will appear?
Well, yes and no. So we have now a few more examples. And actually, maybe it would make sense for me to hold off the answers to answering this question. So in fact, in 2D, we now observed it in a wide variety of models. So, so in particular, for this kind of, for these Rydberg systems, what is important is a constraint, so that they are really constrained model. And what we see that it's quite generic on bipartite lattices in this kind of model. So, but there have been kind of from this many papers that I cited, there have been predictions of scars in very different classes of models. So I don't know if you can call it generic because it's, but, they are so it is, like, there are, I think there are quite broad arrays of systems where these things are present. But for example, we still don't understand, what are exactly the conditions for this. So if you ask me, okay, will this model have scars or not? I would not know before sort of, doing either simulations or experiments. So.
All right, Misha, I think we moved the rest of the questions to the end and let you go on.
Okay, so let me now kind of move on and talk a little bit about our recent work in this involving atom arrays. And so in particular, I will focus on today on how we extend this control to two-dimensional arrays and kind of try to improve, a little bit, the system, the coherence, and, I will try to give a couple of examples, of what we can do with that. It's a kind of a little bit of a sneak preview of what's coming. So, okay, so to move forward, what we have done is we have actually rebuilt our system last year or so, and now we have a second generation of the array working, where the traps are now created by spatial light modulator. So basically, it's we create a computer-generated hologram and then project it in a vacuum chamber, and we have arrays now over the 1,000 of traps. So we can fill these traps, but of course the filling is probabilistic, and we need to sort atoms in these arrays. And the way how we do it, kind of again sort of the emphasizing the idea of parallel manipulation, is we use two crossed acousto-optic deflectors. Instead of one, we now use two, so we can move both rows and columns of the atoms, and it's all of course computer controlled. So there is one other thing which happened, as you all know, and that's kind of illustrated by this picture. It's another historical picture of the team, of the current team. And this was basically the last day in which more than 2 people were allowed in our lab. And so basically, starting from this day, March 17, so we had a period where we basically, could not enter a lab pretty much at all. And, now we are kind of operating in a limited capacity. But what was kind of amazing is that we had like about a week of warning, before the shutdown. And during this week, these guys converted this experiment to completely remote operation. So basically what I will show you in the following, these are basically data, most of this data were, taken completely remotely. So that's kind of new era here. Okay, so here are some examples. So we start with the trap with 600 arrays containing 600 traps, and basically try to load them. And as you see, the loading is probabilistic. So each trap is loaded with something like 50 to 60% probability. So the question is, can we sort? For example, can we fill deterministically 300 sites? So here are some attempts. So this is, initial loading after sorting. Once again, there are some, single shot images. What you see is that with these 300 arrays, it's kind of, there is typically, maybe 1 or 2 kind of errors. So basically, when everything is nice and optimized, so we can fill each trap with probability more than 99%. And it's actually one of the main limitations now is actually vacuum, in our system. But, so for example, if you aim to do experiments with 300 arrays, you can actually still do this, fill all 300 atoms. And the way how we do this filling, we actually take 2 images. We take first disordered image, we sort, and then we take a second image. So in principle, we can post-select. So provided the probability of this, perfect array is high enough, let's say, double digit, we can easily post-select our results to work with perfectly filled lattices. And sometimes we do it, sometimes we don't. So, but the beauty now is that we are in 2 dimensions, so we can actually explore, different types of systems, different types of arrays. So, and here is an example. So, if you would like to fill, for example, arbitrary pattern, so this is a randomly generated kind of pattern or subset of square lattice with 75% filling. So, and here we try it, and it just works. So, okay, so starting from that, we would, of course, have a lot of ideas what to do. And the first idea is to kind of go back to these quantum simulations and ask, if the same Hamiltonian, which I've been describing so far, what kind of phases, can I access? So the easiest phase would be, once again, is when this blockade is basically nearest neighbor. So where you can not just excite simultaneously nearest neighbor, but all of the other possibilities are present. So in this case, you will create a kind of an antiferromagnetic phase, which is, I think we call it checkerboard phase. You will see why it is, so basically when you do this, look at this phase, it's just this phase is up, down in all dimensions. So, but actually it turns out that the system is kind of much richer once you start, for example, changing the range of blockade. So there are, there is a zoo of different phases. So this is a phase diagram, which one of Subir Sajdev's students, Ryan, together with Van Wey and Hannes, calculated, predicted. So, and what we can do now is we can just enjoy exploring this phase diagram. But, one thing that I should point out is that it turns out that, in 2 dimensions, even this Ising, paradigmatic Ising quantum phase transition has never been observed. So let's just try to see how we can, study it and observe it. So we can start now with the square lattice pattern and set the atom separation to sort of be in the right parameter range, and just try to scan the detuning once again adiabatically from negative to positive. And then once in a while we have images like this. So once you see it, you can start characterizing the system. You can ask a question, well, okay, do you always get image like this? No. So can we use some kind of metric to study it? So for example, you can look at something like correlations, and what you see is that on this kind of, on the system of the scale, you basically, this correlation length extends overall system size pretty much. So now we can do different things. We can study, for example, how correlations grow, and that's kind of one thing we could do by using this so-called Kibble-Zuring mechanism, by just taking the sweeps now, which are strictly linear, and changing the time of the sweep. We can see how for longer sweep we have larger correlation, for shorter sweep we have shorter correlations, and we can basically extract this so-called critical exponent. And actually the prediction is that it should be a power law. We actually see quite nice power laws. The critical exponents we see are slightly higher than the ones which are expected for this 2D Ising transition. But actually right now we even kind of have some understanding, develop some understanding why that is the case. So it turns out that one really has to kind of work with large enough system, because this correlation growth is kind of dominated by the interplay between kind of bulk and boundary dynamics. And this is something that we're really exploring right now. But we can also look at the system microscopically. So for example, we ask, what is the defect distribution? And here, what's kind of interesting is that we have a substantial probability on a kind of an order of % of creating this perfect order in systems up to something like, 150 to 100 atoms. So, but, we can also go beyond that. We can, for example, start exploring, transitions into other states, and this actually is a lot of fun. So we can now access, at least 3 or 4 different states. So here is this checkerboard phase, which antiferromagnetic phase we discussed. So this is a so-called star phase. This striated phase is interesting because it actually has, it's stabilized by quantum fluctuation. So this is kind of connected to this Beal's question. So in this phase, you have to have some some variance to be in the kind of in the atom number for that to be stable, and we're actually kind of exploring that now. So, and again, this states you can either study by looking at single shots or by looking at some correlation properties, correlation function, and this is actually something where we have a lot of fun now. So let me just, as one example of kind of new physics one can explore, let me go back to this dynamics and this question of the scars and try to basically answer the second question, which was asked in the intermission. So on which lattices can we create and observe these scars? So what we'll do now, we will start in a kind of wide variety of lattices, and we will perform the following experiment. We'll first create the ordered state, and then we will quench to the, just across the phase transition and see what comes out. And so that's, so this is, I guess it's a hexagonal state, right? So lattice, so it's one of those guys. So this is one example. So we have a state preparation. So it's a bipartite lattice. So we create this, antiferromagnetic state here, and then we quench. And actually what happens is quite remarkable. So basically after some point, the system completely, looks completely disordered, but then you wait a little bit and that actually the order reappears, it's a kind of a complementary order compared to this first, wait till you keep going, and it's kind of really, system, keeps oscillating here. So you can, for example, look at something like sublattice populations to quantify it, and that's what we will kind of use. So these are these oscillations between sublattice. And so what we see is that actually quite a wide variety of two-dimensional bipartite lattices, support this many body scars, So now what we can do is we can ask a question, okay, so what are, how stable, how different are they on different lattices? And because we have these different arrangements, we can really explore it. And so the way how one could kind of analyze and frame it is by looking at the effective Hamiltonian on the system. And so this is this Hamiltonian corresponding to the ideal blockade. It's sometimes called PXP Hamiltonian. And there are all of these corrections. So one actually can kind of recast this by introducing, basically combining terms a little bit, and basically separating the two contributions. One is interactions beyond nearest neighbor. This is a long range term. And another one is what we call imperfect PXP. So it's basically all corrections to the blockade. So then what one can do is one can just try to do these scar experiments on many different lattices. So square, honeycomb, the Lieb lattice, 1D, and then just try to look at the lifetimes of these scars. And actually, quite remarkably, the lifetimes for all of these different lattices tend to be governed, by basically by these two contributions, so they are, so these are the contributions which essentially, correspond to this correction to the blockade Hamiltonian, where n is number of nearest neighbors, and these are this kind of contribution which is due to this next nearest interaction, and so there are some kind of phenomenological parameters one can extract, but actually all of these kind of, different lattices somehow obey this, this relationship. So it looks like that there is some kind of almost a universal model for decay of these scars. But we can do actually much more, and at this point, and we can ask a question: can we improve the stability of the scars? And the way how we'll do it is we'll do it by not just a simple quenches, but the quenches where we, modulate the detuning. So why you even bother looking at that? Well, you could say, basically, generally, if you have some kind of driving, strongly interacting system, it should hit. But there have been a couple of examples recently, pointed out where this is not necessarily the case. So in particular, Some of you might remember a couple of years ago, people have been kind of talking a lot about time crystals. So it's basically a system where you drive periodically, and it responds with the period which is larger than the original driving period. And there was kind of experimental demonstration. So basically, it responds to time translation kind of symmetry breaking, and there were a couple of experiments in ions also in our group in NV Center. So the question we can ask is, can one use similar approach to stabilize many body scars? So the property of this time crystal, which is very important, is that it's stable. This is supposed to be a phase of matter, so it should be a robust kind of process. Let's just give it a try. So here is a simple 9-atom 1D chain quench. You see some of the scars emerging, but now what if instead of just quenching to fixed detuning, you quench to the detuning which changes in time? So clearly what we observe here are two things. So first off, this scar lifetime increases substantially. Second, this kind of scars respond with this with the period of 2t, the twice the period of the original drive. And moreover, if you look carefully, you will see some shifts, some subtle shift in this kind of revival's frequency. And actually, it turns out that this new frequency is exactly 1/2 of the frequency of the periodic drive. So here is, kind of maybe much more dramatic manifestation of that. So here is, again, the same data. You plot the lifetime of this scar, scars driven divided by undriven, and you see that, there is a factor of 2 increase. And there is this kind of frequency locking to this, half of the modulation frequency. So if you kind of start playing with other lattices, honeycomb, even there is this kind of, thing called Karanin. So that's, this is, various lattices which we try to kind of, push the system in various ways. So what you see is really, it's quite robust kind of response. So it's basically very robust subharmonic locking and basically stabilizes this non-equilibrium dynamics where you entangle and disentangle states periodically. So what's the origin of that? We are still thinking about that. So it's kind of a little bit of another experimental discovery, but I think we have some insights, and the insights can be understood as follows. So consider kind of a toy model. This is not a model which we implement the experiment, in which you have a periodic drive where you sequentially apply this PXP Rydberg blockade Hamiltonian and this kind of detuning the phase, just imprint some phase on your system. So so it turns out that if the phase is exactly pi, then because it's PXP Hamiltonian has so-called particle Hall symmetry, basically it should act as a kind of effective spin echo for this Hamiltonian. So basically, it shouldn't matter which state you started with, this state will always revive. That's what happens when phase is equal to pi. But when phase is not pi, all bets are off. And so most the generic states of the system will just, decay and thermalize and everything. But there is some special states, and these are the states from the scar manifold where the response is robust. So with this kind of insight, we can actually check experimentally how robust is our response, and we see that it's actually quite robust, quite dramatically robust. So when you drive the system, if you modulate it slowly, you see a little bit of a response at the same frequency, but once the modulation frequency is fast enough, it disappears, and there is this very strong subharmonic response. And this subharmonic response is robust with respect to driving, lattice spacing, with respect to many imperfections. So basically, from this consideration, we now believe, at least tentatively, that this phenomenon is very much, similar to this kind of time crystalline response, that people have been thinking about. In a sense, it's kind of maybe a new dynamical phase of matter. Okay, so how am I doing on time? Do I still have 5 minutes, Sebastian, or should I wrap up? 5 minutes? Okay, good. All right, so let me then just shift gears and give you a little bit of preview of kind of another direction which we are exploring, and that involves the use of this Rydberg arrays to test quantum optimization algorithm. So for that, let me take a step back and talk about one kind of mathematical combinatorial optimization problem, which is called maximum independent set. The setting is the following. So suppose you are given a graph which have some vertices and edges, and an independent set is defined as a subset of these vertices which do not have connections to each other. So in other words, what you'd like to do, you'd like to color these vertices red, but you cannot color two connected vertices. And so the maximum independent set consists of finding the largest possible number of vertices that you can color. So it's one of these very simple problem, but it turns out to be actually very complicated. So in fact, it is a NP hard problem, and actually for the generic graph, even to find approximate solution is actually NP hard. So here is one example of the graph, which is a special graph. It's called a unit disk graph, where you basically place the vertices wherever you want, but then you connect them only if they're within a certain distance. So this kind of picture is something you probably have seen, if, like remember those times where you could fly still, on the back cover of your airline magazine, pictures like that, So that kind of indicates that this, problem is actually practically important for things like designing networks, machine learning, and it's actually to find exact solution, even for these unit disk graphs, it turns out NP hard. So there are some approximations, there are some, you could do it approximately for certain graphs efficiently, but not exact solution. So if you followed still my talk, you probably kind of realize that this kind of picture, this problem is very much similar to the kind of this Rydberg, blockade kind of idea. So specifically, the Rydberg blockade, remember what we would like to do, we would like to excite as many atoms as possible, but we cannot excite the atoms which are within the Rydberg blockade. So when D is equal to the Rydberg blockade radius, so it turns out that the effective cost function for this problem can be very efficiently encoded in this Rydberg blockade Hamiltonian. So basically, what it means is that, we can, by placing atoms at the right positions, and then subjecting them to some kind of pulses, we can now start exploring, solutions, efficient solutions to this problem. And there are different kind of ways how we can do it. We could either use adiabatic evolution, or we could use something which is called QRA. So let me just give you just a little bit of insights how potentially these things will work and how they start to work. So here is, the idea of kind of adiabatic algorithm. Suppose this is a graph that you would like to find MIS on. So, one idea is that you just basically, set a Rydberg blockade radius in a way which kind of enables all of these connections, which are, written by, given by these links. And then all you need to do, you just need to do the same experiment that I was showing you before. You start in a ground state, go adiabatically across this transition, and then just, make a measurement. So, and then, you have a sample solution which you can compare, for example, for small graph, you can compare it with the, still with your kind of classical algorithms. And so this is an example. So here we, start with the graph, which will have 179 modes. And, MIS here is known. You can solve this graph. The solution is 57. So and what we could do this adiabatic following and look at distribution. So what you see here is that, for this, duration of 2 microseconds, so we can characterize in terms of mean ratio, in terms of also like what's the best solution. So here we quite don't, during this, after this, couple of 100 runs, you still don't find this MIS, but one can now, use it as a basis to start. How does the system performance depends on size of the graph, evolution time, and so on. How this can be optimized. So this is kind of one example showing that some of these answers are non-trivial. So basically, if you increase the evolution time, what we find is that often that there is a the kind of the mean approximation, sometimes starts to go down, but this distribution becomes extremely non-trivial. So here, for example, for long enough duration, you basically after a few shots you find this, MIS. So to kind of really make this all more systematic, what we are now doing is we are basically starting to run this kind of algorithm in a closed loop control, where you basically have, your experiment, which you basically kind of use to create an output, and then you have an optimizer which can control your pulse sequences and so on. So here are some, first few runs, and as an optimizer we can pick one which we want to use. So here is some, very preliminary data where we basically look at runs where we feed it this linear sweep and see what one can, what this machine can do. So we use here this red crab for this example optimizer, which is developed by Tomasa and his collaborators. And so what you see is that this procedure works, but there is some improvement. So this pulse is a little bit different, but this improvement is not kind of enormous. And so what we are still looking is how to basically fine-tune higher parameters, how to explore various optimization approaches, and so on. So here is another example where we employ this so-called QUA, quantum approximate optimization algorithm, where instead of this adiabatic evolution, you apply the sequences of pulses. And here we apply several layers of this these pulses, and you need to choose the parameters of these pulses in an optimal way. So the way how you can do it, you can kind of guess in a smart way, and this we use this guessing procedure, which was developed by the Google group last year, and then feed it into this optimizer and try to see how it performs. And actually, in these instances, we already see that this optimizer can give rise to quite considerable gain. So this performance is still not as good as adiabatic algorithm, but note that the time during which this algorithm runs is like 10 times shorter. So, okay, so it's clear, I hope for you, that we have a lot of fun now with these kind of systems, and we are looking at ways to how to implement deeper circuits, do some serious quantum classical benchmarking, and hopefully identify the graphs which are hard for classical, but maybe easier for quantum solution. So I think I used up my time. So I hope I gave you a little bit of sense. So it's an exciting direction at the interface of many body physics, quantum information science, quantum computing. So, and here's another historical picture of these people, whose blood and sweat resulted in this work, and they're still here together in real life, and they are together virtually, but this is the kind of stuff that they're doing in their free time. So, thank you very much for the attention.
Yeah, thank you, Misha, for this great talk. And I have collected a few more questions, and maybe I start with questions about the limits.
Yeah.
So one question from Aruku Seno was, what is the limitation of the system size? You mentioned something about vacuum, but is it also light intensity, or can you say something
Yeah,
more?
so there are several kind of practical, so basically, there are several things. So first off, on what I have shown you so far is that this Rydberg excitation we have performed basically collectively. So all of the atoms were excited in the Rydberg states at once, right? And so in that sense, we can have individual readout, individual kind of preparation of atoms, but we control them globally, right? But still, even in this global control, it's important that, for example, this this excitation is highly homogeneous, right? So what it really means is that at the end you have some limitations in terms of, for example, power of applied power of this excitation, right, which we now basically excite the atoms from the side by shaping the beam in a very kind of clever way. So, so these kind of enter into, various kind of considerations. So right now, I think we are quite close to the limit, in terms of creating the arrays, we are quite close to the limit, basically, which is given by the combination of our vacuum lifetime and the time which is required to read out the atoms. Both of those could be improved. And so basically, at this point, let's say at the level of 300, atoms, we can sort them out, not perfectly, but, we can have at least, few percent probability that, we get, perfect, rearrangements, right? And so we can sort slightly larger arrays. So some of the data I showed you was, I think, on 18 by 18 atoms, but there we already really start kind of suffering from imperfect preparation, also from kind of variation in excitation powers and so on. So I think a lot of these problems are technical, and I am confident that we should be able to resolve them with the next kind of generation of upgrades. Maybe one problem which is a little bit more kind of important, more, I wouldn't say fundamental, but at a kind of higher level, is that eventually you would like to really control these atoms individually while exciting to the Rydberg states, and that means that you need, basically, arrays of modulators, maybe a few hundred or thousand, of those, which can really, with high on-off ratio, with fast speed, be able to basically create this arbitrary pattern. So this is actually a very kind of non-trivial engineering challenge, and we are collaborating now with groups of Dirk Englund Group and also with Sandia National Labs and with Quera Computing, a startup company to try to develop those. But this is something that I think will be very important in the long run in terms of programmability of large arrays.
Okay, I have one more question from Stephen Mackey. Is it possible to include dissipation into your experiment? Can you look into driven dissipative dynamics?
Yes, yes, the answer is yes. So some amount of dissipation actually is present kind of as is, in a way that, and so our kind of maybe leading dissipation mechanism is the following. So we use 2-photon transition to the Rydberg states, and we excite the atoms from 5s to 6p state. I think I got it right? And then going up, and for example, this p state has a little bit of decay, right? So and we got typically we work in a kind of far detuned kind of Raman regime, so we don't want this dissipation present, but it probably, for let's say the system of a couple of hundred atoms over the entire duration of experiments, you might have some effects of this variety, and actually we are kind of looking now at ways how to mitigate them and maybe even do a little bit of error correction, but I think in particular the direction where this kind of driven dissipative dynamics, which could be very interesting, is this what we sometimes call the Rydberg IT, basically the situation where you kind of have a non-dissipative excitation of individual atoms, but if you have blockade, then you kind of turn on the dissipation. And I think we had a couple of theory ideas, what one could do with them. It's of course something that also Ofer has in his childhood explored, in our other machine at MIT in terms of like photon-photon interaction. But I think this could be very fruitful direction.
Good, Misha. Let me finish with one last question, and that is another question from Bill that actually I had also on my backup question list.
Yeah.
And that is about the improvement of your loading procedure. In Cindy Regan's lab at Gila, they're using this gray molasses loading tricks to enhance their loading above basically 50% before the sorting. So is this an option in your experiment?
Yes, it's absolutely an option, and I can, and I think in a kind of long run, that's probably something that one would really like to utilize. So I must say that we tried a couple of times to kind of add this procedure to our, we have all relevant lasers and so on. We have not really made it, and we saw that one can improve this, probabilities somewhat. We have not yet been able to kind of implement it at scale that would really kind of make a difference for our, system, so, but it's definitely something, it's on our list. And, I very much hope that we will, there are kind of just practical questions, which, this here's devil is in the details. At a high level, yeah, absolutely, that's, if we can boost the procedure, we can work with large array, absolutely. But, there are things also, for example, how you sort the arrays, it's kind of a little bit non-trivial, right? So, but once you have a very few kind of imperfections, you could really, kind of greatly parallelize the sorting and kind of really speed up everything. So it would help, But so far, we have made few attempts, and I can say we did everything systematically, but so far it has not been as helpful as we hoped for. But I think it's a matter of time.
Okay, thank you, Misha, and thank you again for this great and inspiring talk. And I hand over to Sebastian.
Thank you, Misha, again, also from my side. Very cool talk. I'd like to take this opportunity to remind everybody that we will have our very first Young Researchers session on November 5th, where we'll have 3 short talks by you guys. If you have done something new and cool, you should go ahead and tell us about it. Go to the nomination page on our website for all the details. And if you haven't already sent us an email, please do so by October 5th. Next week, I'd like to remind you there will be no quantum science seminar. Peter Zoller's talk has been moved to October 8th. And if you want to get notified about what we do, please go to our website, quantumscienceseminar.com, subscribe to our email list or Google Calendar, follow us on Twitter, and you should certainly check out our sister seminar, the AMO seminar, where tomorrow our very own Andrew Daly will be talking about dissipative many-body dynamics with cold atoms. So if you want to join us for a follow-on Q&A session with Misha, please join us in the Zoom link that I just posted on the YouTube chat. That, I'd like to thank you for your interest, and we hope to see you again, not next week, 2 weeks from now, same time, same place. Bye.